Good afternoon. Thank you to all to being here. This is the 8th Antonio Picariello Lecture, and please, Beppe, I thank you to Beppe Longo, that is the coordinator or the data science and the real organizer of this lecture. And please, Beppe.
Thank you very much, Flora, but you are the organizer. I'm just, the old guru. I'm the wise man, but that's it. It's matter of age, that's... So, okay, it's a pleasure for me to introduce Kai Polsterer for several reasons. First of all, because Kai is one of the leading data scientists in the field of basic science data analysis, but he is also the other side of the medal. As most of you know, I am an astrophysicist who turned data scientist, while Kai is a computer scientist who turned astrophysicist. So basically, we are the two different approaches to astroinformatics, and Kai has done some of the most amazing contribution to the field together with his collaborators. He is in fact team leader at the prestigious Heidelberg Institute for Theoretical Studies. I must say I've been there several times. One of the most beautiful, most friendly research institutes I ever visited in my life. And he is also an influential member of the International Virtual Observatory, and also he has done important contribution to the software pipelines for many instruments, scientific instruments. He is also the project scientist of the most advanced public outreach facility in Europe, which is the Supernova Center at the European Southern Observatory in Garking. So basically, in spite of his young age, he is one of the most prominent figures we have in this field in Europe. And I am very proud and honored to call him a friend. We have been friends for many years and we'll be friends for many other years to come. So I think this is basically it. And also I want to add something. I am sorry for those who are not here, because Kai, in my opinion, is one of the best lecturers I ever heard. He is clear, convincing. He is really an outstanding speaker. So I'm looking forward to enjoy this lecture, and I hope you will do the same. So Kai, to you, the screen, the stage, the microphone, you know how to handle this better than me.
I hope so, Pepe, and I hope you see my slides now.
Yes, we do.
And many thanks for the warm introduction, and I must say I blush a little bit and get red. Yes, you put a lot of pressure on me for that talk. I wouldn't say I'm outstanding. It's just that people in the field of astrophysics say, oh, he's a good computer scientist. And those in the field of computer science say, oh, yes, he must be good in astrophysics, because everyone talks about a domain they are not aware of. That's why people might think I'm a clever person. But I leave it up to you to judge it. But first of all, many thanks for the invitation and the opportunity here to present in your data science class in this memorial lectures. And yeah, I feel a little bit sad about not going to Naples, because as you said, Pepe, we are good friends over the years, and there are many better places than Germany for the moment. But with Corona, traveling is not allowed, and I hope for the future that we will meet. So you asked me to talk a little bit for the class about something that goes in the direction of interdisciplinarity and has a focus on statistics in order to sort of fill the whole set of great lectures you organized. So that's why I'm today presenting a talk where I talk about photometric redshift estimation and how this helps to improve weather forecast. I would like to give an interdisciplinary view on machine learning and how machine learning bridges between a lot of different communities. Now, actually, it should go to the next slide. Here you see Sauron's eye, or what you would call it. It's this famous image that was shown for the supermassive black hole at the beginning or at the end of 2019, and it was a really breakthrough because it's like observing from here in Europe something that is as tiny as a needle somewhere in New York. And it's a tremendous effort to observe something like a supermassive black hole or an AGN. And the big question is now, how are supermassive black holes actually connected to something as Earth-bound like weather forecast? And the thing is, not through physics, even though there are some people claiming that through supernova activities or AGN activity, there might be reasons why we had ice ages in the past, but that's not what the talk is going about. It's about commonalities and methodology, bridging between those different fields of research. So, like in many fields, it's the same in astronomy. There's too much of data. It's an avalanche. Yeah, that's what people say. I always say it's not the amount of data you're looking at, because already a simple Excel spreadsheet with 60,000 rows is too much if you don't know how to program Excel correctly to find the cell where two values as a sum give a certain result. So it really depends on what you want to do, the complexity of the data, and what you want to achieve scientifically in this question. Machine learning is often referred to as the magic tool that solves everything. That's not true, but it helps a lot. You will see soon after. And as I see from at least one smiling face, people are experienced with that. So a lot of people expect machine learning to do wonders, but that's not what machine learning is about. It's not about a magic wand, it's about statistics, mathematics, and a joint work in different fields of research. So here in astronomy, and I thought for a mixed class, it's also good to give a little bit background on what we actually do in astronomy. We have a lot of missions. Currently ongoing is a Gaia mission. It's a satellite mission, as you can see on this image, that currently tries to measure very precisely the position of 1% of the 100 billion stars we have in our Milky Way, in our galaxy. And we want to do it to estimate distances. And this gives us something like a petabyte of data, a lot of data. But it's not only coming the data from observation campaigns or satellite missions, it also comes from simulations. There are a lot of different sources that generate data. And here I'm just mentioning the illustrious simulation, a simulation of the evolution of the early universe, and it generated roughly 1 petabyte of data as well. But if you now look at the future of astronomy, we are so crazy that we build phased radio antenna telescopes that are quite large and collect quite a lot of data. Here we talk about something like an exabyte per day. Of course, this is a little bit unfair because this is the raw data coming out of the dishes before it goes into correlators, but already at the raw level, at the raw data level, you want to apply sometimes machine learning to tag data to get rid of certain kind of inference patterns. So it's really data intense, but it's not only in astronomy. In all other fields nowadays, with the advent of computers, with digital detectors, we are now collecting so large data sets that we just know how to store it at the moment, but don't have a clue how to efficiently analyze it, at least for many challenges we are facing in sciences. So one solution in order to address the problems we have is to solve regression problems. Regression problems help us to estimate or calculate or derive certain physical parameters we in astrophysics need to actually do a physical analysis and to get some physical understanding of what's going on in the universe and to understand processes in detail. And I just have this simple equation, and for those of you now feeling bored, and most of you know what a regression is, I think it's so fundamental to repeat it over and over again to understand how things are connected, and it will soon get more complicated. what we have here is our model F that defines how, based on our input features X, we want to estimate our output values Y. And this clearly defines a stage. We have some input data X, we have some predictions Y we want to generate, and therefore we need some training data where we have X's and Y's in our example. And in astronomy, we have now many examples where we actually need to solve the regression problems, because for a lot of reasons, it's too expensive to do detailed observation campaigns, or it's too technically complicated or challenging to actually measure all values directly. So we indirectly want to evaluate and estimate values based on other measurements we already have. So this is a brief introduction what it's about, regression problems to solve and deal with large data sets. Here now a brief introduction to all of you that are not astronomers. And I guess I'm right, most of you are not astronomers. Is this correct, Pepper? Yeah.
Yes,
okay, so what we are now talking about are supermassive black holes. They are also referred to as active galactic nuclei, because in nearly all galaxies, in the center of nearly all galaxies, we have supermassive black holes. And those supermassive black holes, even though they are black holes, they are among the brightest sources in the universe. How does it happen? Here in the picture, you see an example of Centaurus A, and there's an overlay to the green disk of the galaxy. You see in red some radio emission. The radio emission created by the inner core of the galaxy, by the active galactic nuclei, often exceeds the diameter and size of the optical counterpart of the galaxy by a factor of 10. They are huge in the radio. And what makes them so huge is in the core, where the supermassive black hole is, matter is accreted, it spirals in, heats up, and with an efficiency of 10 to sometimes 20%, mass is directly transferred into energy following Einstein's equation, E equals mc squared. If you look at a usual star, the efficiency is around 1%. So this process of heating up material and creating radio emissions and other hard X-ray emissions causes actually that those quasars are seen in the radio as quasi-stellar sources. That gave the name to them because we saw point-like sources in radio images and we're wondering what they are. But the reason behind it is it's a far, far away galaxy where this jet points in our direction and gives us a sharp point. So because they are now so bright, they are of extreme interest to us in astrophysics because they allow us to observe the very early universe. They allow us to go back in history and understand how things evolved in the universe. And even though this might be boring for you, I always get extremely excited when talking about those beasts because it's really huge beasts with masses of millions and billions of solar masses, supermassive black holes accreting material. And so those black holes are the brightest, among the brightest objects in the universe. So what is now important for us is to get data. So all I'm talking about in this lecture now about is the Sloan Digital Sky Survey. And this telescope, when it was built up, was completely different than any other telescope before. Here on the picture, you see the Apache Peak Observatory, and on the left-hand side, you see the telescope. And it has not the usual shape and the usual structure, and it's not a dome opening, it's just a shack moving over it to cover it when it's not in use. And this telescope was just built with one purpose, not to be a highly precise instrument, but a data-intense instrument that harvests data from the whole sky and collects and makes a screenshot, or what you would call it, from the whole sky. Create a survey that is put on disks and made available for analysis in data science. So what were the breakthrough changes back then is, if you look on the left-hand side, you see an image of the CCD detectors, of the camera array that was used for observation. And as you can see, there are 5 different rows of detectors. They are with different filters, going from the ultraviolet to somewhere close to the near infrared. That's why they are called UGRIZ, those filter bands. And now the telescope was just placed on one position on the sky, and the charges on the CCD detector were moved in parallel with the motion of the sky. Completely different, like a usual telescope that would move to point on a certain spot. Here, the charges on the CCD detector moved and were read out with the same speed the sky was moving across. And this allowed to precisely scan the whole sky and do images in 5 filters, not RGB like you would do with your camera at home, but in 5 filters, images of the whole sky. And based on that data, sources were selected for a detailed follow-up study. So imaging gives us broadband filter information that gives us a rough distribution of the spectral energy distribution to see how much energy is in which filter band. While spectroscopy is something you can think of like a genome. Yeah, by doing spectroscopy, you disperse the physical information transported through the light. You disperse it into distinct lines that tell you a lot about physical processes. And to do it, they had a very clever idea. Here on the right-hand side, you see at the front is the backplane that connects to the spectrograph that takes the data. And on the lower part, you see a plate. They created from alloy certain plates that were fitting exactly a patch on the sky. They drilled holes at the places where they had galaxies or quasars or stars they wanted to take data from. They pre-assembled and attached roughly 700 fibers to that plate. And before the night, they just pulled in the whole machinery and took a whole night long spectrum, because this is a huge difference. Taking images is really quick. Taking spectra takes a lot of time. And if you want to take, of all the billions of sources we have, spectra, you need a long time to do it. So that's the reason why regression problems help us a lot. We have broad information from photometry, but we want to derive physical properties you usually would get from spectroscopy. So, and now let's go into the data science section, but I thought it's essential for you to roughly understand the setting. What is the question we are physically interested in, to understand how do we get the data, where the data from we are talking about, to understand what we are doing next. So if you now look at what we want to do is we want to estimate the so-called redshift based on those 5 photometric values. And here in this example, you see redshift is an expression comparing a laboratory wavelength, lambda 0, to the measured wavelength of a certain distinct emission line. And 1 plus that equals this. So if you now look at the image, you see the wavelength plotted against a flux, and you see 2 spectra of 2 different quasars. One with a redshift of 3.81, that's the one that is a little bit more shifted to the left, and one shifted to a redshift, or at a redshift of z equals 5.31. And what you can see in the background are the quantum efficiencies of the 5 filter band, the UGRIZ. And here, this prominent peak at the beginning of the spectra is a so-called Lyman alpha line. And for the z equals 3.81 quasar, most of the emission is in the R band, while for the higher redshifted one, more is in the I band. And you can see spectra with a higher redshift are moved to the red. They are redshifted towards reddish bands. If you now look at the 2 images of both quasars, it's really hard to say by looking at the images what is the redshift of the source, but you will soon learn that by the quality of nearly 1%, we can estimate it, and that's amazing. So if you now take training data, all the spectra from Sloan, because with the spectra, you have something like a ground truth. You have something that is physically measured, and you have a redshift Z extracted from the spectra. On the other hand, you have something like the photometric values together with it. So you now can define an excellent training example. And in this image here, you see now a stack of a lot of different spectra of different sources sorted by their redshift. And you see how the prominent lines shift further to the red. So it's really a continuous physical process you try to map with your regression problem. So photometric redshift estimation here means, as a model, we use for the beginning k nearest neighbors by looking at your vicinity based on your input features. In this example, it's magnitudes. It's fitting a certain model on the energy distribution based on the images. So you get 5 magnitudes out, magnitude in U, G, I, R, Z, and you can use it now to derive something like the redshift. That's what we want to estimate in our example. And the challenge, whatever you do, is you want to evaluate your performance because you want to compare yourself. So there are many different scoring functions that are actually used. You have something like the root mean square error, commonly used. If you want not to have too much emphasis on the individual outliers you might want to use the median absolute deviation. You look at how much bias does your prediction have? What is the standard deviation of your predicted, or the errors between the prediction and the true values? What are the max errors, mean errors? A lot of different things are used. And there are a lot of diagnostic tools. I personally prefer the visual ones. On the right-hand side is a commonly used tool that actually makes use of plotting the spectroscopic redshift on the x-axis against the estimated axis on the y-axis. So we do photometric redshift estimation on 70,000 spectra in Sloan's data release 7. I think by now we have data release 16, but this is something like 10-year-old work. And you get a lot of point predictions. The perfect prediction would be the diagonal of this quadrant. But as you can see, it's spreading and we have certain errors. So the question now is, actually, we don't want to predict a redshift. Actually, we want to deal with uncertainties. And where do uncertainties come in? So we have something like model uncertainties. In this example, it's not given through the way we define our model, because k nearest neighbors doesn't have a model uncertainty, but it's given through our training data we use to train our model. Because if the training data covers everything and doesn't have has a proper sampling of the physical environment we are interested in, then it's useful. Otherwise, all the biases and errors and uncertainties we have in our training example just get learned by our model and therefore will be used in our predictions. We have input uncertainties because our measurements have measurement errors. For the example I'm giving today, this is left out, but those are things you can deal with, Monte Carlo methods, for example. And then, of course, if you have uncertain models and uncertainties in your input, you want to have uncertain estimates. And this means, it's quite simple, from predicting a single precise redshift Z to a single value, you want to predict something like a probability density function, PDF, that gives you probability density for each individual redshift, because this has a lot of nice side effects. If you have a PDF, you can start asking yourself, so what's the probability of the redshift being in between A and B? And that just means you integrate over that and you get your probability out to be in a range between two values. And this is actually the question you want to ask yourself when you want to do physics. Give me all objects with a redshift of larger than 5 with a probability of more than 80%. Because you want to incorporate actually the uncertainties you allow for your estimates within your scientific analysis. And this enables you to keep it. Because if you just do a prediction to a hard value, you're no longer able to actually disentangle that, because your decision was made based on thresholds in the past in your model, and therefore all uncertainty is lost. If you now look at this plot, I know it's a little bit confusing, but it's very easy to understand. In this example, I plotted for one particular quasar. On the x-axis, you see the redshift. The red line marks the true redshift of the quasar. I now plotted the nearest neighbors based on K and N, and I think it's the nearest 32 neighbors for that source, or 64 for that source. And you see the individual gray dots on the top, because now based on similarity in the feature space, objects were selected, and we are looking at their redshift. And what we see now is that we have the true redshift somewhere around 2, but in the background we see, oh, the redshift distribution seems to be a little bit complicated by looking at the neighbors. Now people started to deal with uncertain predictions already a while ago, and back then Antonio Di Santo started his PhD thesis with me, and he wanted to first do predictions sharply, and we came up with it would be nice to have some uncertainties in the prediction, and then we started checking what are common tools actually to check the quality of your uncertain predictions. So people often do things like they simplify things that give a lot of information. So if you now have a probability density function, in this example I plotted a source where you can't decide between two values. It's something simplified from the example before. And you can see if you now have a multimodal distribution with two likely peaks, and you just use the mean by using the root mean square error to evaluate it on your PDF, then it just takes the center of it. And it's like having a self-driving car approaching a traffic light. It's not a good example, actually, if I think of Naples, but in any other part of the world, it's a good example.
You still remember it, right?
Yeah, no, because I always say if self-driving cars survive Naples, they are ready for the market. No, if a self-driving car's approaching a traffic light and the traffic light switches from green to yellow, then you have two options. You either break down or you stop or you accelerate. Yeah, the peak in Naples would be higher for the acceleration part, but it's not a good solution to stick with a medium speed in the middle, then you will crash. So sometimes it's better to report uncertainties correctly and to evaluate them correctly. So the question is really, if you take something like a root mean square error that simplifies or oversimplifies everything, is this the right way to evaluate something complex as a multimodal probability density function? The other thing I've seen a lot is people start stacking probability density function of individual sources. So for each source, you get out a probability density function. You shift it by the true redshift, so you can align them. And you just look at the redshift deviation. And here in the example, you see it on the left-hand side. You have a single narrow peak. And for the other example, you have a single narrow peak as well. One is below, one is above. The likelihood of at the true redshift is nearly 0. So it's a really bad estimate in that case. But if you now stack all those together and in the end look how much are exceeding a certain range, how many outliers you have, it's meaningless because it's not telling you anything, because in the end at the true redshift in the center, you had a likelihood close to 0. So your predictions are not really good. And the other thing is if you take two broader examples, it's improving, yes, but you already see something in the outlying parts. If you have multimodal distribution, it's getting worse. So we really have to think of what is a proper description of uncertainties. So the question here, is it correct? I usually hate slides that are filled with equations. And here I have to talk about some essential terms called calibration and sharpness. Tilman Gneiting, a colleague of mine, introduced them. And calibration, I really have to read it, refers to the statistical consistency between the distributional forecast and the observation, and is a joint property of the prediction and the observed values. We know it as biases, we know it as slanted and distorted things. Sharpness, on the other hand, refers to the concentration of the predicted predictive distribution and is a property of the forecast only. This is really how narrow is our prediction. And those are things we want to be honest about. Here at that point, Tilman Gneiting introduced back then proper evaluation tool, the CRPS, the Continuous Rank Probability Score. And it's very visually and easy to understand. You take a PDF. Here in this example, the prediction is the black line and the red line is the true redshift. And you take the PDF and transfer it into a cumulative distributive function. The CDF of the true redshift turns into the Heaviside step function that is 0 until the true value and jumps immediately to 1 at the true value. To calculate the CRPS, you now just look at the surface area between both functions, between the CDF of the point, the true redshift, and the CDF of your prediction. And by looking at that, you now see the sharper your prediction gets, the closer you get, the surface area shrinks because the CDF becomes steeper. On the other hand, if you shift it, you add a lot of surface area. So being peaky but being offsetted means you're not getting it correctly. It was introduced for temperature forecast, but it's really helpful to evaluate things. Another proper evaluation tool is the so-called PIT, the probability integral transform, or its histogram of it. If you take a CDF and look at it, and take the CDF at a given true value, the true redshift in this example, then in this example, the true redshift has a CDF value of 0.75. And you now do exactly the same for all your forecasts. If you do so, you get a U-shaped distribution in the underdispersed case. So if your forecast is like saying, tomorrow temperature in Naples is 10 degrees plus minus 50 degrees. It's in my margin, but it's so unprecise that I very likely hit my predictions always at the upper end or at the lower end. So I get a lot of zeros and a lot of ones. So I get this under dispersion, this U-shaped thing in the histogram. If I'm saying tomorrow temperature in Naples is 15.83 plus minus 0.0001 degrees. So I'm starting to lie at you and make it artificially narrower. It's then it's under dispersed. It's too narrow. I get the outer ones, and it's over dispersed when I was broader. Yeah, I got the examples wrong in that case. Sorry for that. So if I'm broad, I always hit it in the middle. And if I'm too narrow, I'm always outside, like you had seen in the example before. If I have a bias, yeah, I see lower values are preferred or higher values are preferred. Then I have a slanted one. Only when I have a uniform distribution, I know my predictions are well calibrated. And therefore, this is a very simple visual tool together with the CRPS. The PIT helps me to check how good is my calibration, while the CRPS allows me to measure how good is my calibration as well as my sharpness. How precise am I and how well am I calibrated? So now let's look at some results and using proper tools to evaluate it. Here in this example, I did exactly the same like I did in the beginning, like I did 10 years ago. So Antonio did this in this experiment actually. So we took a single Gaussian and just claimed the uncertainty of the prediction. So we took the mean using the k nearest neighbors, looking at the mean of the nearest neighbors, and said this is a mean value. And we just said, okay, the uncertainty is fixed to be 0.01. So we don't know what the uncertainty is. We are just making it really narrow and claim we are very wise people and know how to predict it. What you see in the PIT is it's extremely under dispersed. It's just too narrow. We are not giving you a correct answer. And the CRPS tells us something, but it gives us a comparable value. So if we now go to the next slide, you see what happens if we say, okay, Antonio, 0.01 was lying at me. Give me another guess for what is a good uncertainty. And you say, oh, let's use 0.0. So without having a clue about the uncertainty of our model, actually. Yeah, then you see the PAT changes its shape. Yeah, we are now a little bit over dispersed. We are too broad in our prediction. And we have outliers at the end, at 0 and 1. That comes to the more complex structure of the distribution. But the CRPS improves. And so does the plot on the right-hand side. The plot on the right-hand side changed from being point estimate to now show something like on the y-axis showing the integral over the probability density. So if you now take k nearest neighbors, you actually can get an estimate about the standard deviation in the predicted space, in the redshift space, by just looking at your k nearest neighbors, calculating the mean for your prediction, and calculating the standard deviation over the nearest neighbors. And this allows you to adaptively, for each candidate, assign an individual nearest neighbor. And as you can see in this example, it also improves. So if you see now, lying about uncertainty doesn't help. CRPS is just improving if you are getting more honest about what you predict. And that's what you also see in the PAT. You already see when you are lying and you are under dispersed or over dispersed. So if you don't have a clue about the uncertainty, PAT will reveal. The reason why we didn't further improve at that point is, and it doesn't depend, of course you can tweet about models. K nearest neighbor is a simple model, but here is something fundamental talking about a concept of evaluating things. If you remember the example I showed you a few slides before, here you can directly see we have multimodalities. A single Gaussian will never be able to capture the complex redshift distribution we are actually facing in our example. And for that reason, a single Gaussian will never work out to explain the complex data. Now think of it. You use a k nearest neighbor model. You get the nearest neighbors out, and then you fit a Gaussian mixture model with 5 Gaussian components to your nearest neighbors. Then you are able to build more complex distributions. Here in the example, you have seen 5 Gaussians. You have seen how 5 Gaussians can be used to sort of, in a compact form, describe the probability density function or the actual redshift distribution of the nearest neighbors. And if you now train a model to do so, you can now create predictions that are actually the parameters, or you fit a Gaussian mixture model and you get a model-based description of your probability density function with 5 mu's, with 5 weights, and 5 sigmas, with 5 standard deviations. So now you can go a step further. Now you can go from k nearest neighbor to something that is ensemble technique. If you take a random forest, it's an ensemble of individual decision trees. And usually you would evaluate a random forest by calculating something like the mean over your individual decision trees. But if you have individual decision trees, you can actually use the results of each individual decision tree as input to fit a Gaussian mixture model. This is something called quantile regression forest. And it allows you to use an ensemble technique that uses bootstrapping and bagging and other things to make a proper representation of your data set, actually, and you can use it as a basis to estimate your probability density functions better and better. And what you could see over all the examples is now the PAT becomes more and more uniformly, the CRPS drops, and the plot becomes more like a line. And those are steps going further and further to improve uncertainties and uncertain estimates. Back then, we thought, okay, using features is one thing. Deep learning seemed to be cool. Back then, Antonio, when you did it, I think it was 6 years ago, 5 years ago, I don't know. Everyone was doing deep learning. And so we thought, oh yeah, let's do it on images.
4 years ago.
5 years ago, yeah.
4.
Yeah. 4, yeah. When you published, but we worked on it beforehand. But yeah, so we were bored, and we had all data is free in astronomy, but free doesn't mean accessible. There are public interfaces, but it's really hard to access things. And the good thing in astronomy is that there are at least some standards that are available. And the International Virtual Observatory Alliance, IVOA, provides those standardization processes. And they use a helix tessellation of the sky as a basis to create something they call the hierarchical progressive surveys, HIPS. Yeah, astronomy also has a lot of acronyms. Please excuse that. So back then, I wrote a simple interface that makes use of this representation. It's something like Google Maps. You have hierarchically where you can zoom in to different levels and extract data. We used something based on that to actually extract images for each individual source and use the images as input. And with this, Antonio built the DCMDN, yeah, the deep convolutional mixture density network that has 2 parts. It has a deep convolutional part, it's the left-hand side of that plot. This is an ordinary convolutional network that is just having the task of learning a set of features, actually. Instead of using engineered features like the photometric magnitudes we were using before, we now said, let's take a convolutional part to learn those features and use the mixture density network introduced by Bishop, I think in 2000 something. Use the mixture density network that is just taking input features and produces as outputs the mu's, the sigmas, and weights of a Gaussian mixture model. And this just demands in the description of your loss function that you ensure that the integral, so the weights sum to 1, and that you don't have negative sigmas. So you just had to ensure certain properties to make sure that the parameters actually describe a probability density function, which integral has to be 1. So with this, we now had an architecture that could take images and produced a set of parameters for a Gaussian mixture model and used that. And we had been back then the first to actually use the CRPS now as a function to optimize the network, not the log likelihood like it's very common or other losses that are very common. We really use the CRPS, a proper scoring rule that is taking care of calibration and sharpness. And with this, a simple mixture density network based on features already performed much better. If you now carefully look on the right-hand side, you see it's a log sum probability density in the plot, in the color bar. Before that, it was the summed one. And we had to switch to a log because otherwise it was just looking like a line. It's really very precise in the predictions now. And with the DCMDN, we even further improved the predictions, now using images instead of just plain features. And the multimodalities you can see is given through the degeneracy of the physical problem we are facing, that at a redshift of 0.0, sources also could have a redshift of 2. You can't distinguish just having 5 plain broadband filters what the actual spectroscopic redshift is. So it's not physically doable. And as you can see now, through simple steps, introducing proper scoring functions and going even further to training a network using a proper scoring function, we could further and further improve the prediction quality and make sure that we have properly calibrated uncertain results as an output. Antonio back then put my image and the image of a dead rotten fish in the trained network, and this is really a limitation. The network got trained on images of galaxies or quasars, and now if you put me in or dead rotten fish, you can see my redshift is 1.7 and the redshift of the dead rotten fish is 0.3. That tells you I'm 10 billion years old. I know that's a lot. But of course it's correct because fish don't live as long as humans. So it's just saying if a network isn't trained with proper data, it will produce crappy shit. So the uncertainty in the prediction doesn't help you with that. It's just more precise for the proper case. But now the big step. How does it connect to weather forecast and weather forecast simulation? We were back then learning everything about proper scoring rules from a group at HITS that does statistics, that works on weather forecasts. And we had some chats and I explained what our problems are. They introduced us to the concept of proper scoring functions and all the things, with a lot of coffee, of course. And after we were finished, we actually had a chat in the different direction, because now we knew how to use neural networks to solve those tasks. And the tasks they were facing, they were looking at data of the European Center for Medium Range Weather Forecast, ECMWF, hard to pronounce. And I just plotted a few parameters. Here you see on the left-hand side a temperature map across Europe. And you see pressure, air pressure over Europe. And on the right-hand side, you see cloud coverage, wind direction, and wind speeds. But this is just a few of the actually used 18 parameters. So what they get in simulations is a grid of 81 times 81 grid points across Europe. And they get it 50 times because they run the simulation with slightly changed input parameter 50 times. And they get out 18 parameters, of which only a few I really understand. But that's not necessary if you talk about methods. In this case, yeah, the task is actually to do statistical post-processing. If you now have 50 predictions, which of those predictions should you take to actually predict the temperature at a particular station? And in this example, it was to predict it for 537 weather stations across Germany, where you have a latitude, a longitude, an altitude, something orography tells you about the structure and land, and whether it's on land or sea. And it's a forecast always 2 days ahead. And for the 18 parameters, they were just condensing the whole ensemble of 50 values to just a mean and a standard deviation interpolated to the exact position of a particular station. And they used the data from 2007 until 2015 for training, and completely out of sample did the prediction and the testing on 2016. With this, with the best method published so far, they reach a COPS of 0.81. Then we gave the code we developed to them, and they just figured out, oh, we don't need the convolutional layer. We just put in the values we have. And that's how they published it. Sebastian Lerch and Stefan Rach published it in 2018, yes. And they just took the fully connected part, put in the temperature at 2 meters, mean and standard deviation, as well as the auxiliary parameters, plus allowed for an embedding to provide some station-specific correction terms. And then they fed in the data, and, well, where is it? No, the result isn't shown. Where's the result? It's sort of not showing, but they already got a very good result to publish. At that point, it was so good that it's now also becoming a highly cited publication, because it's a completely new way of doing post-processing of weather forecasts. And the next steps we thought about now is, okay, let's go a step further. So what if we take the parameters for a station and build up a simple network? Then we can compress it to 2 values. This gives us the ability to start doing a physical interpretation of what the network learns. And if you now compress the parameters of the stations to 2D and use a 2D for coloring it on the right-hand side on the map, you see particular regions in Germany. It's not only coastal distance, it's also, if there's a Rhine Valley at close to Heidelberg, all these regions pop up, and you now can start using the data provided through the network as a reason to argue why the network improves and what the network actually captures. You can start to understand and learn what the network is doing. And then we actually wanted to do the DCMDN approach and figured out we don't have enough compute space. We have a decent institute. But if we really want to put the whole ensemble in, where we have 50 ensemble members times 81 times 81 times 17 physical parameters, because one didn't make sense at all to us, and you have 535 stations, but the problem is you only have 3,600 days for training, you figure out you don't have enough data to train such a large and complex architecture in the end. So we thought of using different strategies. In this example, just plain autoencoders. Those are networks taking the input data, go through a bottleneck in the encoder part, and then try to decode from the 2D and reconstruct the original input data. And by doing so, it learns a compressed representation of the original data. If you now do it, and in this example, I took temperature, pressure, cloud coverage, wind direction, and wind speed. So 6 free parameters, because wind direction has a X and Y component. So 6 free parameters. And here in the example, you see on the upper left, you see a day in February with cold weather and cloud coverage, and a day in August where it's much warmer across Europe. And on the right-hand side, you see 2 different reconstructions. All the blue points in the represented 2D plane that comes from the bottleneck of the autoencoder here represent where the cold winter day go, and the red point correspond to the warm summer day. If you now train the network and you let it run, you see it picks up some structure, but it's still so complicated that compressing it to 2D really makes no sense at all. It allows you to learn at least there are cold days that are in the blue corner, and there are hot days that are in the red corner. And as I said, the 50 points correspond to the 50 ensemble members. So it doesn't really help. And if you now look just at temperature, and I'm wondering why it's so flickering here on my screen, I hope you can see it sort of fine. It also, by looking at temperature, it just learns there are cold days and warm days. It's really complex data, and we just have 3,000 days for training. That's nothing for such a complex question or challenge. But what we did is, so far, we took the architecture they had by then and added this location term, added something, a compressed representation of what is the overall cloud structure, where do the dew points look like, and what's the temperature, in order to somehow reproduce something like a weather regime, so that you know the simulation model that generates the forecast for certain weather regimes. If you have the Azoren Islands, you have this high pressure regime there, then you have to underestimate or you have to overestimate. It gives you some understanding of where the simulation model has problems, and it helps you to learn to improve your forecast. So coming to the end of my 50 minutes, it's time to conclude. So I know I was very detailed in the beginning, but I thought it's necessary to understand it. So in this example, I wanted to motivate. Often there are scientific questions you want to work on. You can't directly work on because you don't have the measurements directly. So in this example, it's about photometric redshift estimation, and to be more precise, in a probabilistic way. Back then, when we did this, we learned everything that was done so far in astrophysics to evaluate it was not the correct thing to do. And it helped a lot to talk to people from a completely different domain, to talk to people from weather forecasting and to talk to statisticians. And this is really one of the core messages. It's so much fun dealing with data, but it's even more fun talking to humans. So find someone that knows much better how to evaluate things if you can't do it properly. So back then, based on the CRPS we implemented the DCMDN, and that was a big step forward in improving the precision. And I come to that in a second. We used it now by sharing the code, and that's the other big message. Talk to others, but share what you have done. By sharing the code with the statisticians, they could isolate the part they were interested in and used it. And thereby, our work on quasars, photometric redshift estimation of quasars, helped to improve the weather forecast. And I hope all of you figured out that the weather forecast got much better as last year. So coming to an end is, it sounds ridiculous, but uncertainty is necessary to be more precise. If you do evaluation, if you do predictions, it's sometimes better to be honest and say, this is a value I estimated, but I actually don't know how precise it is. It's often very critical to give just a point estimate, because a lot of people will rely on that point estimate and take this particular value as a true value. If you provide uncertainties, it helps a lot, and it makes your science more precise. Really choose the right score for training and evaluation. Use proper scoring rules, proper for what you are scientifically interested in. And yes, as I said, data science is very interdisciplinary, so let's learn from each other and have fun with each other. So towards the end, I would like to acknowledge those that were on that endeavor with weather forecasts and AGNs with me. So it's Antonio joining the talk, as well as Sebastian Lerck and Tilman Gneiting, who had hits in Heidelberg. Or Sebastian now has his own group in Karlsruhe, actually working on the topic we started with. So many thanks for your attention, and I'm ready to take your questions.
Thank you very much, Kai. And well, it was interesting as usual. And okay, Flora, you are leading the discussion.
Thank you. Thank you, Kai. Thank you. Really interesting.
Is there any question?
I hope it was okay. You told me 50 minutes, so I made it 50 minutes.
That was perfect. You are one of the few people who are
absolutely, absolutely.
Okay, let's. Yeah.
I have a question. Hi, it's Miguel Livenri. First of all, thank you for the great lecture. So my question is about the work that I'm doing with Stefano Gavuoti, that you probably know.
Sorry, I can't hear you.
Can you hear me?
Yeah, now it's better. It was sort of stuck.
Okay, so my question is about my work that I'm doing with Stefano Gavuoti. You probably know him.
Yeah, of course I know Stefano.
Yeah, so we are doing basically optimization of the best solution taken by different methods that produce PDFs. And while I have demonstrated that I'm able in an unsupervised way to optimize the point estimate, I'm still puzzling on a way to optimize the PDFs. And the reason why is that I don't have a metric that can estimate clearly as how good is it a single estimate over the full range, right? Because if you have an ensemble of PDFs, then you can use something like the CRPS. So I'm asking you if you have an equivalence of what we use, like the delta norm for point estimates, but for PDF, or what would you use if you wanted to select the best PDF from a group of maybe 6 or 7 PDFs produced by different methods? Thank you.
So I hope I got you correctly. Let's summarize what you asked to be sure that I answer the correct question. The question is, or at least as I get it, you're producing through different methods several different PDFs. And now in the end, you want to know which one of the PDFs is the one to trust, right?
Exactly, and thus I need a metric to do so.
For a single source, yeah. And here's the challenge is, you can evaluate over a whole set of predictions for a lot of individual method, of a single method for all predictions. You can evaluate which method performs better. But if you now have 5 different predictions for a single source, it's like having 5 different point estimates for a single source. You can toss a coin. The only thing you should do is compare the methods. What you can do is you can say in a certain range of values, certain methods perform better than others. And that could be used to choose the best result. So you can look at those behaviors, but there is no statistical way to directly now decide if you have 5 uncertain predictions. There's no direct way of saying this of the 5 is the best to choose. But you can mix all predictions together to create a large ensemble out of them and use this as an ensemble technique. But to choose the right one out of 5 competing results of 5 competing methods is nearly not possible.
All right, thank you. I mean, of course, my opinion is different because we are trying to do it. But yeah, thank you very much.
No,
this issue will be very nice for a sort of roundtable with the statisticians in our team. I mean, we have outstanding statisticians like Roberta Siciliano, Giuseppe Pandolfo, who could, you know, provide us with some means. I mean, it could be. Kai, why don't we organize a roundtable to discuss this issue?
Yes, of course. Yes, of course. But then I think the question should be formulated differently. If you just have for a single source 5 predictions, there's no way to say which of them is the correct one. So
I agree on that.
Perhaps we should have a discussion beforehand before we do a roundtable discussion on that.
Yeah, I mean, wait. Unless you have a measure of error, right? Because if I have, for example, 5 photometric redshifts and the true spectroscopic one, I can estimate which one is the better one based on its distance.
Oh, of course. Then you can calculate it, which method is best for that particular example. But you can't do it in order to predict it, because if you predict, you don't have a true redshift. If you predict something, you don't know the true value. And if you have 5 uncertain predictions, which one to choose, I can't say. Because you just can evaluate a method on a comparable sample or on the same sample, then you can evaluate with which method is better. You can even say a method is better in the lower range of values and in the higher range and use this as a decision point. You can even find other things there, but if you just have 5 uncertain predictions, no way.
So at the end of it, we will need a sort of measurement of how good is it a PDF by itself. That will give us the equivalence of a distance for a point measure.
Yeah, or you train another network that just learns to pick the right PDF. And this will automatically learn in which range, which network to choose.
Yeah, I'm doing so, but you need to have a measure of what's the right PDF, and that's a problem by itself.
Yes.
Yeah. Do we have other questions? I mean, I think that this remote modality really is killing the interactions. I mean, it's
Pepper, I know from all things I'm organizing.
Exactly.
It's completely different if you're standing after a lecture in the front and students come to you and ask you questions and you go for a coffee with them. I know. Nothing.
It's a sort of an intimidation, I mean, to speak in front of a flat monitor, also for people who listen. So, again, is there any other questions? Okay, it seems like there is not. So, Flora, I think we can call it over. Let me thank first Kai for being here, giving these lectures, and it will be posted on the YouTube channel of the Laurea very quickly. I also remind the students that to register for the credits, and the letters are ready and should be distributed to the various departments in a few days. So thank you very much, Kai. It was really a pleasure to virtually see you after such a long time, and we hope to have you again soon. Flora.
Thank you. Thank you, Prof.